Deja vu, I just been in this place.
Hi, I'm Felix and I'm in charge of the drive system.
Calling you and the searches of.
Hey, I'm Jacob and I'm in charge of the dribble kicker system.
Deja vu, I just been in this time.
Hey,
And the searches of mystery.
Hey, I'm Amarish and I'm in charge of the navigation system. The Queensland University of Technology Robotics team have been tasked to participate in the RoboCup Small Size League. The project tasked the team to assemble a robot that can score as many goals within the time while conforming to the Small Size League rules. The specifications of the robot is that it's able to navigate itself around the field without any assistance.
An omnidirectional drive was chosen for this system, capable of holonomic movement in 3 degrees of freedom. To achieve this, 3 super cheap, brushed 120:1 plastic gear motors were selected due to their insanely budget-friendly price at $7.30 each. The main chassis was 3D printed using a grey PLA filament, designed as a single piece to incorporate snug mounting for all components to minimize play and add rigidity to the design. Custom Omni wheels were designed with a large 84mm diameter to ensure that performance of the motors met the required maximum speeds. In testing, the Pololo plastic gear motors underperformed in speed requirements. To fix this, the gearboxes were kept but motors were swapped out with an alternative high current, similarly 130 sized motor, rated for 3 times the torque and twice the speed. Afterwards, the drive had no issues beating minimum and maximum specifications required by this platform, while costing a staggering $11 per wheel motor module. Control is achieved through 2 DVR8835 Pololo motor controllers mounted to a custom PCB. These converted GPIO outputs from the Raspberry Pi to motor duty cycle and direction. A kinematic control model then determines exact duty cycles and direction needed by each of the 3 individual motors.
hi, my name is Jacob and I'm in charge of the dribble subsystem. The purpose of the dribble subsystem is to be able to maintain control of the ball as the robot maneuvers around the field. The purpose of the kicker subsystem is to reliably kick the ball at range at least twice a minute. A solenoid kicker was chosen for the kicker subsystem as it shows you have a high output for what we desired. The solenoid kicker featured a boost converter and a charging circuit. The boost converter had to step up the voltage from the voltage regulator, and the charging circuit had to build up charging the capacitor, and on discharge of the capacitor allowed for it. For the dribble subsystem, a tapered style was chosen for the shape as it proved to be the best for maneuverability, and inlets were chosen for grip as they seemed to be the best option because they dribble a minimal surface area as well as covering the whole dribble. The dribble was also driven by a belt drive system using rubber band and a DC motor as it proved to be the most efficient.
The vision system is the primary source of sensory data for the robot. It enables the robot to detect other objects in its environment, such as the ball, obstacles, and goals. The robot sees through a live video feed of a camera situated on the front. Each frame is downsampled to increase processing speed while retaining the same field of view. It is then converted to the Scilab color space to help alleviate the effects of shadows and glare. Because the real size of the objects in the camera's field of view is known beforehand, the robot can estimate a range and bearing of the object in the image. Running at only 8 FPS and being susceptible to changes in arena lighting, this algorithm could have been improved upon through experimentation of other computer vision techniques such as adaptive thresholding. Other approaches such as convolutional neural networks and Haar cascades were considered but required too much upfront work in tooling setup and recording and labeling to meet our development schedule.
The AI navigation system can be thought as the brain of the robot, as it describes a system that can perform tasks requiring human-like intelligence. The system essentially depicts how the robot will behave in the environment. However, depending on the approach to design, the system does have its limitations. While planning design follows the potential field method. The idea of this method is to allow the robot to generate a field of the environment and determine the best possible route towards the objective. The type of agent designed is the model and goal-based reflex agent. Essentially, the agent takes input from the perception sensors to generate a model and determine the best choice of action to achieve the goal. The following set of scenes show the results of the design agent in a simulated environment. The scenes showcase various objectives and cases the robot will face and display how the robot will approach each scenario in relation to the specifications. Problem case scenarios such as local maxima and minima and ball behind obstacles are handled similarly and efficiently. This is approached by placing a virtual object that is placed near an obstacle, and it is temporarily until the problem case is avoided, and allows the robot to maneuver around obstacle to reach the actual objective. Overall, the integration of the entire robot as a cohesive unit was incomplete, but given more time to work on the project, full functionality of the robot will be easily completed and the robot will be ready for the Cup. The project was conducted by Group of 17 and we hope you enjoyed the video.